start in some seconds.
Okay, hello everyone. I'm Mihai Pon from Bayreuth University, and I'm the moderator for the next lecture given by Robert Berman. Now, our speaker here is a professor at the University of Gothenburg. He's interested in complex differential geometry, Monge-Ampère equations, and mathematical physics. He will lecture on emergent complex geometry and the gauge-gravity duality. I hope you'll enjoy the very nice lecture to come. Thank you.
So, hi everybody. The title of my talk is Emergent Complex Geometry and the Gauge-Gravity Duality. Right, okay. The goal of the talk is to describe an application of the probabilistic construction of Canonical metrics on complex algebraic varieties to quantum gravity. So this is an approach to Canonical metrics that I've been playing with for quite some years, but today I really want to explain this more recent application to quantum gravity. So that's a joint work with Tristan Collins and Daniel Persson here. So what it does is that it provides something of a physical interpretation of this probabilistic construction, which was really, I originally developed it in the context of complex algebraic geometry and canonical metrics. So this physical interpretation is new. So let me first give you some physics background. So this is something of a tourist guide, if you want. Okay, so as you know, I'm sure you know, the forces of nature are separated into the gravitational force, which dominates at large distances. And then on the other hand, you have the electromagnetic force and the weak and the strong nuclear forces. And they dominate at small distances, like on the level of atoms and so forth. Okay, and the latter ones are gauge theories in contrast to gravity. So very briefly, gauge theories in a nutshell then. So in a gauge theory, the matter fields, so these are the classical fields which describe electrons, quarks, and so forth. So they are functions on space-time, which is R4. And they take values in representations of SUN. So this is the gauge group. So this is the point with the gauge theory, that is that you have an action of the gauge group. So to really get down to the physical content, one should at the end mod out this symmetry group, the gauge group. Okay, and in the standard model for these three forces, up to, the electromagnetic force up to the strong force, this n is actually at most 3. So it's actually 1, 2, and 3. Okay, so for the strong force, QCD, which describes the interaction of quarks, n is 3, and this 3 is precisely the number of quarks. They are just 3 fundamental quarks. Okay, so these gauge theories were first described classically in terms of fields, as I mentioned. So for n equal to 1, that's Maxwell's theory of the electromagnetic field. And then Young and Mills came up with this gauge theories for n, 2, and 3, basically. Okay, but then eventually in the 70s, they were quantized. So these theories are described in terms of quantum fields. So if you want to get back to the classical fields, they sort of emerge as collective states of quantum particles. Okay, and these quantum particles are described by probability distribution. So we'll come back to probability distributions later on. But this quantization procedure, unfortunately, it failed radically for gravity. Okay, so let me remind you about gravity. So according to Einstein, gravity is described by a metric on space-time, so R4, but with a Lorentzian signature then. So time here plays a special role compared to the 3 space coordinates. Okay, and the matter and the energy in the universe, it curves space-time, R4. So what it does is that it really affects the Ricci curvature of the metric. Okay, but in the vacuum, the Ricci curvature is constant. Okay, so it doesn't have to be 0 because of the cosmological constant, which is like a uniform background field in space. It can be non-zero, but it's always constant in the vacuum. So the Ricci curvature is constant. Anyhow, if you would like to quantize this, then the metric should be replaced, so that the metric is the classical field in the story. So it should be replaced by particles, quantum particles, which will be called gravitons, like in this picture here, where you have the particles somehow quantizing the geometry of space-time. But that doesn't seem to work very well, as I mentioned. But a very influential approach to quantum gravity, which is completely new compared to the classical one, was initiated by Juan Malacena in the late 90s. Okay, so he came up with this idea of the gauge-gravity duality. So let me remind you, in the gauge theories of the Standard Model, the gauge group is SUN, but only for n up to 3. These are the 3 classical forces. Okay, so, but then you can ask, I mean, what physics emerges if you just take this general theory with the gauge group SUN and then you let n tend to infinity? So this question was basically asked by 't Hooft, and Malacena's answer is that gravity emerges. So that's the idea of the gauge gravity duality, is that gravity is somehow described by a gauge theory, surprisingly enough, but gravity only emerges when n tends to infinity. For finite n, somehow gravity is hidden, but when you let n to infinity, you see it emerging. So the picture you should have in mind is a bit like if you had n particles in space-time, located in space, really, and these are discrete objects, but when n tends to infinity, somehow it's as if they curve space-time and geometry emerges. Okay, so that's the way gravity would emerge from this gauge theory. But there is an important but, is that in this theory of gravity that Malacena considered, it has to be supersymmetric. So it's a supersymmetric gauge theory to start with. So I'm not going into the technical details of that, but very roughly the point is that in general there are 2 types of particles in a quantum field theory, the bosons and the fermions. In a supersymmetric gauge theory, there's a symmetry, the supersymmetry, relating the 2. So for any boson, there will be a fermion. Anyhow, if the gauge theory is supersymmetric, accordingly, the corresponding emergent gravity should also be supersymmetric. So what does that mean concretely? So in geometric terms, when you're considering supersymmetric gravity, space-time, ordinary space-time, is complemented with extra internal dimensions. Okay, so your space-time is now the exterior space-time cross a compact space S, which is the internal space. Okay, but I mean, physically, you don't have to think about it in terms of extra dimensions. These internal dimensions, they really encode the particle content. So you can just think of the internal space as geometric representation of the particle content. And the classical vacuum in supergravity is encoded by metric on this internal space S with constant positive Ricci curvature. So the metric G is an Einstein metric, but there's also an extra supersymmetry condition which in mathematical terms means that this metric is a Sasaki metric. So I won't really go into the precise definition here. Okay, but not only is the gauge theory in Maldacena considered supersymmetric, it also has a conformal symmetry. So that means that there is a scaling action by R plus, scaling all the lengths in the theory, in the gauge theory. And it turns out that on the gravity side, it induces an extra dimension in the emergent external space-time, which is thus 5-dimensional, because the original gauge theory is in 4-dimensional space, but the gravity really emerges in 5 dimensions. And this 5-dimensional space is really hyperbolic Lorentzian space, or what is called ADS5. And you can think of it as just R4 cross this R plus. So in this picture, R4 is on the boundary, and then when you move along R plus, you go into the interior. Okay, so that's maybe a bit annoying if you really want to describe gravity in 4 dimensions, like in our world. But that's not really a big problem, because if you want to get the 4-dimensional emergent geometry, you just have to work with a 3-dimensional gauge group. But for simplicity, I would just stick with the, 3-dimensional gauge theory on a 3-dimensional space-time. So, but I will stick to gauge theories on 4-dimensional space-time for simplicity. So the emergent gravity is 5-dimensional. So that maybe sounds a bit strange that you get an extra emergent dimension in the space-time, even an external one. But we can just say that the motivation really comes from the holographic principle that 't Hooft came up with before Maldacena. And the motivation comes from, if you want, from black holes. So if you want to describe a black hole, the interior here of a black hole is the space-time you want to describe. But it's not really accessible because of the event horizon. And the idea then of the holographic principle is that you should be able to describe this space-time, the black hole interior, with a theory living on the boundary in 1 dimension lower than, because you don't have access to the interior. And in Maldacena's picture, then this R plus the conformal scaling, geometrically what it does is that you can think of it as taking you inside the horizon somehow, formally. At least that's where the extra dimension emerges. But the gauge theory really lives on the boundary, which in our case is just ordinary R4. Okay, so okay, but here we shall really focus on the internal compact space S, which encodes the supersymmetry. So the picture is that you have the external space-time whose boundary is R4, but then the supersymmetry is encoded by this interior space, and the supergravity vacuum is encoded by an Einstein metric on this compact space. And we should really focus on the geometry on this compact space, which in this case is really the non-trivial geometry that we want to study, because the geometry of this hyperbolic space we do already know. Okay, let's see. Right. Okay, but then the question is, how much supersymmetry is needed? Do you really need supersymmetry? Ideally, maybe you would like to get rid of supersymmetry. So Maldacena originally assumed maximal supersymmetry. So on the gravity side, this means that the internal compact space S is homogeneous. It has maximal symmetry, so it's actually a round sphere. Okay, but then people looked at gauge theories with minimal supersymmetry. So you can't get rid of all the supersymmetry for the moment, but you can consider minimal supersymmetry. And on the gravity side, this means that the corresponding internal compact space S is a just general Sasaki-Einstein manifold. Could have a very complicated topology, and so forth. But it's expected that the gauge gravity duality prevails also with minimal supersymmetry. Right. Okay, so the question that I'm concerned with is, can one construct the quantum state in the rank n gauge theory on flat R4 space-time such that the supergravity vacuum emerges, the Sasaki-Einstein metric emerges as the rank n tends to infinity. Okay, so I mean, you can think of this as a quite non-trivial test for the gauge gravity duality, because if you can write down a quantum state in the gauge theory such that in the large n limit this supergravity vacuum emerges, then that's a quite good test somehow of the correspondence of this duality, because this metric is rarely explicitly given and it's not homogeneous in any sense. So if it emerges, it's not somehow by coincidence, I guess. Right. Okay, so the result is, in a nutshell then, that yes, there is such a canonical quantum state, and the classical in geometry, the supergravity vacuum emerges in the large n limit. But there are some technical caveats that I will briefly mention. Okay, so let me describe the ideas involved. So the starting point of the construction of this quantum state is a general feature of supersymmetric gauge theories on R4, namely their low energy behavior, which is the behavior we're interested in here, is actually determined by what is called the moduli space of classical vacua. So very briefly, what that is that you can think of in this gauge theory, you will have some matter fields, phi1 and so forth, which are a bit like the quark fields in the standard model. And there is a superpotential W describing their interactions. And this moduli space of classical vacua is just the critical points then of the superpotential. But because of the gauge symmetry, you also have to mod out the gauge, the action of the gauge group, which you can think of as roughly SUN. Okay, but in this particular case of a superconformal gauge theory of rank n, it turns out that this moduli space of classical vacua is very concrete. It's just a symmetric product of a complex cone Y. So what I mean with that is that there is a cone Y. I'll give you the precise definition in a second. And the moduli space of classical vacua is just the space of the configuration space for n points on this cone. And that's the classical vacuum. Okay, so I mean, typically, if you want to think of this slightly more concretely, is that these matter fields, phi1 and so forth, they're just n times n matrices. And what this moduli space of classical vacua is that it parameterizes their joint eigenvalues, given this condition that we're looking at the critical points of the superpotential. So that's how the symmetric product appears here. Okay, so what about this complex cone? Well, what it is that it's a complex affine algebraic variety with an isolated singularity, like in this picture here. And in this particular model we're looking at, it turns out that the complex dimension of this complex variety is 3. Okay, but there's also scaling action by R plus on the gauge theory, as I mentioned, and this induces a repulsive action by R plus on Y. So the group of positive numbers R plus acts on Y simply by some scaling, but fixing this singular point. Okay, but then the base of the cone, which is really the hero in the story, is defined by just you remove the singular point and you just take the quotient by R plus. So that will give you, you can't see it here, but it will give you a compact space, which is the base of the cone. And okay, so just to remind you that, I mean, now we're starting with the gauge theory, and we want to see gravity emerges, how gravity emerges. At this point, the moduli space of classical vacua, what it gives us is that it is the space S where gravity will emerge. It's the base of the cone emerging from the gauge theory. This is the space S. But for the moment, it doesn't have a metric. And the problem then is to see how the metric emerges as well from the gauge theory on this space S. So this will be the internal space of the space-time. And then it turns out that this r plus orbits on the cone are actually related to this extra dimension, which appears in the external space-time, but I'm not going into that. And the final ingredient is that y also comes with a non-vanishing holomorphic top form, which has positive degree with respect to the scaling action. Okay, so that's what the gauge theory gives you directly. Okay, just to make this concrete, let's consider the case of maximal supersymmetry. So in this case, the complex cone is really just complex affine space itself of 3 dimensions. So it's C3. And this is actually the only case where y is non-singular. So in this case, there is no singular point. It's just the origin, which plays the role of which is the fixed point, because there is an r plus action, which is just a standard one, scaling C3. Okay, and then when you take the quotient to get the base by this r plus action, you just get the unit sphere, which makes sense because the maximal supersymmetry should give you a completely homogeneous internal space for the internal space. And finally, in this case, the holomorphic top form that I said always comes along is just the original, the standard one here. Okay, so that's the case of maximal supersymmetry. Okay, but then let me give you some more interesting examples with minimal supersymmetry. So a good way to get minimal supersymmetry is to let y be just the zero locus of a homogeneous polynomial of degree 3 in C4. So that will now be a 3-dimensional complex algebraic variety. And the important thing is that this polynomial be homogeneous, because if it's homogeneous, the zero locus will be invariant under the standard r plus action, so it will be a complex cone. And then this degree 3 condition comes up because you want to find this holomorphic top form on y, and it turns out that under this degree assumption, you can just take it to be a the natural top form induced from the ambient one. So I'm not going into the precise definition. So here's a picture. Somehow a real slice of the situation. So here is the complex singular cone y, and then you get the base S topologically. You get it by just intersecting y with the unit sphere in C4. So that will topologically be the same thing as modding out the action by scaling of r plus here. But more generally, you don't have to take the intersection with the unit sphere. You could just take the intersection with a level set where any radial function r equals 1. Okay, so radial function would just be a positive function which has degree 1 with respect to scaling. And all of these will topologically give the same internal space S, which is called the link of the singularity here. But the problem is that we really want to construct the Einstein metric on the space. Okay, so now the crucial geometric fact that we're going to exploit is that the Sasaki-Einstein metric can be readily recovered from its volume form, dV. So that's the good news, that in order to see, in order to see how the metric emerges, we just have to see how the volume form emerges from a quantum state of the rank n gauge theory. Okay, so the plan then is we're going to introduce a canonical quantum state, psi n, and its probability amplitude will induce a random point process with n points on this space S, from which the volume form we're looking for will emerge in the large n limit. So physically, you can think of this as representing an ensemble of n quantum particles in this rank n gauge theory, which are a bit like quarks, but n quarks somehow. And then in the large n limit, the volume form will emerge. That's the idea. Okay, so let me see. Right. So in general, a supersymmetric quantum state of the gauge theory is described by a holomorphic function on the classical vacuum moduli space. So in this case, the classical vacuum moduli space is a symmetric cone, a symmetric product of a cone, and we're looking then for a holomorphic function on this space. So you can think of that as the complex wave function somehow of the quantum state. Okay. So I mean, if we have once we've found such a state, what we want is to consider the corresponding probability amplitude. So that's just the modulus square of this state, and then you just multiply it with this reference volume form on Y. Take tensor products. So the point is that, as I told you then, that Y comes with a holomorphic top form, and if you wedge it with its own bar, you can get a volume form on the symmetric product. Okay, so that looks good. So you might want to just say that let's try to sample points with respect to this measure. But the problem is that in general, I mean, the total integral of this total integral will diverge in general, because Y is non-compact, and because of the scaling action and holomorphicity, this will always diverge. Okay, but that's not really a problem, because what we really want is to take the quotient by R star to get down to the compact space. So if we manage to construct this measure in such a way that it's invariant under scaling, then we can identify the measure with the probability measure on this compact quotient space once we normalize. Okay. Right. Okay, so we're going to build this state from polynomials, and we want it to be invariant in the way I mentioned. Okay, so to build this state, I will denote by hk of Y the space of all the vector space of all polynomials on Y of degree k. So you can just remember, you can just think of this cone as an affine algebraic variety inside an affine space, and we can restrict polynomials on degree k to this variety, and that will give us this space hky. And I will take the n, the rank of the gauge theory. I will take this particular sequence of n's which appear as dimensions of these spaces. Okay, and the reason is that for these n, such an n, I can first write down the Slater determinant, which is just the determinant you form by taking a basis in this space, psi1 to psi n, and forming this determinant here. So this is in the physics literature, it's called a Slater determinant. So that will be a holomorphic function on Y to the n. But that's not our canonical state, because our canonical state will be defined as a fractional inverse power of the Slater determinant. Okay, so why is that? Well, the whole point is that taking this fractional negative power will make sure that this measure we're looking at is invariant under the action of R plus on Y. And the point is that, I mean, if we normalize, then this volume form here, this omega part has degree 1, and psi n itself has degree k. So that's why we need to take this negative fractional power to get degree 0 with respect to scalings for this measure. Okay, and the final remark is that you might want to think that this construction depends on the choice of basis here in the Slater determinant. But if you change the basis, all that happens is that this psi n will just get multiplied by an overall complex constant, which will be irrelevant in the following. Okay, so now we have our canonical probability measure, which lives on the quotient space, the n-fold product of the quotient space S. So that's just it's just this measure we're looking at, and then we're descending it to S to the n. And finally, we just normalize it to get the probability measure. Okay, but then there is a catch. There's still a catch. It's not completely clear that the total integral, even on the compact space, will be finite. And the trouble is that because of this negative power here, it may actually blow up even if the space itself is compact. So there is no problem now with the infinity, with the divergence at infinity, but there could be divergence inside this compact space S. Okay, so the conjecture we pose then is that if you assume that Y is quasi-regular, which is just, that's a generic property, so I'm not going into what that means. But if we assume that, then our conjecture is that the probability measure on S to the n is well defined for large n, if and only if S admits a unique Sasaki-Einstein metric. Because the point is that in general, there are actually abstractions to the existence of a Sasaki-Einstein metric. And the conjecture is that the abstraction really comes from demanding that this state be normalizable. Okay, but if we assume that that is the case, that it's normalizable, then we have a canonical probability measure. We can sample n points on our space S, and the conjecture then is that when n tends to infinity, when we look at the corresponding empirical measures, that's where you put Dirac masses at n random points and normalize by n. And the conjecture is that this will converge in probability towards the volume form of the unique Sasaki-Einstein metric. Okay, so that's the meaning of being able to, in that sense, I mean, the classical geometry, the supergravity vacuum encoded by the Sasaki-Einstein metric really emerges from this quantum state in the gauge theory. But that's a conjecture we make. And our main result, what it does is that it proves this modulo analytic continuation in a certain sense. Okay, so why is that? And the problem is that, as I mentioned, is that this state we're looking at with the integrand of the probability measure is very singular in general. So because of this negative power here, it will blow up at the zero locus of the determinant here. So it will in general blow up. And that's why its total integral may in general be divergent. Okay, so what we do is that we introduce a regularization parameter called beta, and ideally would like to take beta equal to -1, but we will take beta positive, and we will study the large n limit for such a beta, and finally we will do analytic continuation to beta equal to -1. That's how the volume form of the Sasaki-Einstein metric will emerge rigorously. Okay, so to state this result is that for a given beta positive, we define these deformed probability measures by introducing this beta. So let me remind you then that beta equal to -1 is the canonical case. Okay, and then the theorem is that if you assume that S admits a Sasaki-Einstein metric, then for fixed positive beta, the corresponding empirical measures, when you sample n points on the space S, the empirical measure converges in probability towards a volume form now depending on beta. Okay, but the next observation is that this volume form is actually real analytic with respect to beta down to negative beta, in fact, all the way down to beta equal to -1. Okay, and if you then analytically continue it from positive beta down to beta equal to -1, then that's actually the volume form of the Sasaki-Einstein metric. So this is the way we prove that the Sasaki-Einstein metric emerges in the large n limit. Here, yeah. Okay, so I will actually skip that slide and just then discuss the problem of existence of Sasaki-Einstein metric. So it's actually known now since a couple of years that S has a Sasaki-Einstein metric if and only if this complex cone is K-stable. So that's an algebra geometric condition of stability, which appears in the context of the Yao-Tian-Donaldson conjecture in complex geometry, which in this case was established by Collins and Seculati a few years ago. So it's actually known then when Sasaki-Einstein metric exists. Okay, so but then there's another result by Fujita Odaka, which you can use to see that if this canonical state we're looking at is normalizable, so if the interval is finite, then that actually implies by algebraic geometry that y is k-stable. And then by this resolution of the Sasaki-Einstein, of the Yau-Tian-Donaldson conjecture, this normalizability actually implies then that there is a Sasaki-Einstein metric on S, as we conjecture. Okay. So, but unfortunately, the converse implication is widely open for the moment. Okay, so recently I actually gave a new direct analytic proof of this implication, which doesn't pass by the solution of the Yau-Tian-Donaldson conjecture or any algebraic geometry actually. I should also mention that previously a completely different gauge theory interpretation of k-stability has been given in a work by Collins, Shi, and Yau. But that's a completely different approach than linking k-stability to the gauge theory. Here. Okay, so finally, you might ask if analytic continuation is really needed, because as we saw here, if this state is normalizable, then that actually does imply that there is a Sasaki-Einstein metric. So you could actually try to sample with respect to the corresponding probability measure and hope, as we conjecture, that the Sasaki-Einstein metric will emerge without any need to do this regularization and analytic continuation. Okay, so to give you a result in this direction, first consider the partition function in the setup. So that's just the normalizing constant as a function of the beta. Okay, so beta equal to -1, let me remind you, is the canonical case, but then to make sure it's integrable, we can consider positive beta. Okay, so then the theorem is that the convergence as n tends to infinity towards the Sasaki-Einstein metric without doing any regularization, it actually holds under the following condition. So there should first of all exist an epsilon such that not only is this partition function constant as we need to assume, but because we need to assume it's constant. It's finite for -1, so it will in particular be finite all the way up to positive beta. But we also make a growth condition how it grows with n. Okay, so this is satisfied in some examples. So that's a natural assumption. But the more serious assumption is that when you allow complex beta, so you can think of this as a holomorphic function with respect to beta, which is holomorphic in this strip over the domain where it converges. Okay, so that's now a holomorphic function for complex beta. And the more serious assumption is that it's actually zero-free, maybe not in the whole strip necessarily, but in a neighborhood of this interval. So the fixed neighborhood independent of n. So what we want to exclude is that there will be zeros which accumulate around -1 and up to 0 as n tends to infinity. That's what we want to exclude. So in statistical mechanical terms, what this means is that the theorem proves that the convergence holds if there is no phase transition as beta passes from beta positive down to beta equal to -1, because the accumulation of complex zeros is almost the definition of a phase transition in the sense of Li and Yang in statistical mechanics. So to wrap everything up, let me show you a simulation which I think illustrates a bit what's going on. Let me tell you about the simulation which takes place in R2. So that might be a bit surprising because our compact manifold S is 5-dimensional, if you remember. But then we'll consider the case now when Y is toric. So that's a special case So this means that there's a three-dimensional torus acting on our space S. So in this case, we get the torus vibration essentially over R2. Okay, as you see in this cartoon picture, it projects down to a flat space, which in this case is R2. Right. Okay, and then what happens then is that the volume form we're looking for of a Sasaki-Einstein metric on S, if it's T3 invariant, it will correspond to a density on R2 here. Okay, so we get the density on R2, but unfortunately, in general, it's not explicitly known, even on R2. Right. Okay. And so likewise, we can mod out the T3 action when we sample the point on S. So in this way, the rank n gauge theory in this Toric case, it will give rise to a random point process with n points on R2. Okay, and the good news then is that their probability law, when we sample on R2, that's explicitly, no, I mean, we get an explicit formula in this case. So that's completely explicit given n. Okay, and the other good news is that in this case, there's no problem with divergences once we get down to R2. Okay, so that's good. That means that we can sample in R2 just using standard dynamical Monte Carlo techniques because we have this explicit law. So very briefly, the point when you sample dynamically is that you start with, in this case, a uniform distribution of points on a square. And as time goes on, you eventually reach the desired distribution of points in R2. Okay, so the simulation I will show you now is courtesy of Rolf Andreasson. So in this particular case, the complex cone will be the blow up of the complex projective plane at 3 points. Right. So in this simulation, we start by sampling a uniform distribution of points on a square, which eventually with time, as you see, gets deformed. So where it's blue, that means that there's a high density of points in that region. So you see as time goes on, eventually we'll reach some essentially stationary distribution of points, which is the desired distribution of points we get when we sample n points. So then by taking time averages of this, eventually what you get is a distribution whose profile looks like this in R2. So this is then a candidate for the volume form of the Sasaki-Einstein metric we're looking for. But then, I mean, you might wonder, I mean, how do we know it's the correct one? Because, as I said, it's not explicitly known. Well, what we do then is that we go back, let's go back to the simulation. And here we've drawn a graph of the Mabuchi functional. So it's known that the Sasaki-Einstein metric, its volume form minimizes the Mabuchi functional. So we check here if what we get eventually does minimize the Mabuchi functional. So that looks promising. It seems to at least be a stationary point here. But then, I mean, in the rigorous proof, what we prove is that in the large n limit, the volume form we get really minimizes the Mabuchi functional. So that's the idea of the rigorous proof. And more precisely, what we prove is that we get the large deviation principle, where the rate functional is the Mabuchi functional. So that means that the probability of deviation from the minimizer is actually exponentially small, and the minimizer is the Sasaki-Einstein volume form. Okay, so I think that's all I had to say today. So thanks for listening. Thanks.